Okay, good afternoon, everyone. Today's speaker, I don't think needs any introduction, but for the sake of formality, today we have Professor Erol Tutumluer. He is he holds the Paul F. Kent and Law Faculty Scholar and serves as the Director of International Programs. His research interests include the characterization of pavement and railroad track geomaterials, modeling of granular foundation system using innovative techniques, sustainable use of foundation geomaterials and construction practices for transportation infrastructure, discrete element analysis of ballast, dynamic response measurements and analysis of track systems, and mechanistic analysis and design. That was
That's a lot.
Dr. Tutumluer has served as investigator over 70 research projects and graduated 17 PhD students, 34 master students, and has authored or co-authored more than 300 peer-reviewed publications. Please welcome Professor Tutumluer.
Thank you, Jaime. Indeed, it's a pleasure to be here with you guys. I really appreciate the invitation for this CAN seminar presentation, and I've been working on transportation geotechnics. That's my field, as most of you know. But you also need to know that my affiliation with aggregates, our work and research work on aggregates and affiliation with aggregate industry in general goes way back to my PhD years. So starting from early 1990s, I got involved in aggregate research, and what I will talk to you and share about actually goes as old as probably my PhD days in some of the slides. But then throughout this period, all the work we have been doing, and I've been involved with the International Center for Aggregates Research, and continuing on with that kind of focus on aggregates into 5-6 years of my chair position of the AFP 70, the Aggregates Committee of the Transportation Research Board, and probably over 15 years of service for that committee. Now I'm the section chair at TRB. So it's an ongoing thing, and everybody here knows me already as an aggregate person. I will have to then take you through a really, I think, engineered use of this product, this aggregate, especially from an unbound aggregate layer perspective. And that's why I wanted to start the series of presentations maybe on this pavement type, which is what we call as inverted pavements. And I will go through some of the basics, as well as I will go through in my presentation some developments and case histories and how actual projects were done out in the field. So again, that goes along with my career word, I guess, affiliation and involvement with the aggregate materials. All right. Also want to say that all along these years, of course, many students, many co-authors and co-workers, students and research colleagues got involved in this work, and on and off I will be highlighting and giving referring to their names as colleagues from both industry and researchers. Just as a starting point, a few slides I have to mention to you about how aggregates are the building blocks used in everything we build. Transportation facilities, roads are what we build, and aggregates are used in both bound and unbound layers. Especially I will focus on as unbound in this application, but will reflect a lot on the bound final surface courses, of course, as well. And the idea is aggregates are always in high demand. It was up to maybe a certain 7% growth rate in the way that aggregates were actually looked at the worldwide marketplace, construction aggregates in general. Right now, as of recent numbers, I found 5.2% is the current annual growth rate of about maybe 51.7 billion metric tons. They're projecting as for the production or the needs in 2019. In the US alone, we have over 3,700 quarries, sand and gravel, sand, gravel, and stone producers, basically, and nearly 2.5 billion metric tons were produced in 2016.
And if you look at the industry scorecard publication of the National Stone, Sand and Gravel Association, NSSGA, on their website, that's at a value of about $27 billion, contributing almost maybe 5 times that value to the overall U.S. gross domestic product. So what I will talk about has to do with some unbound applications and engineered unbound applications in inverted payments in my presentation. So if you think about all these production numbers, 27% approximately of the crushed stone produced and 23% of the total sand and gravel produced annually in the US are used as base course materials, pavement base course construction. So we're very familiar in general with what this is, a conventional flexible pavement scenario where we see the unbound aggregate layer in the middle, right? That's a typical pavement design. A lot of the low volume, medium volume roads we build, a lot of the local roads go with that simple design scheme. So the philosophy being the weakest material is at the bottom subgrade and you build up those stiffer layers, and unbound aggregate cost-wise, at any point you can say, of course, depends on the price of the oil, 4 to 6 times cheaper than usually building an inch of an asphalt. That's the inch of an aggregate base. We take advantage of aggregate material, crushed stone, especially high quality crushed stone, taking the loads and distributing the wheel loads, and basically carrying all the loads as support for the stability of the hot mix asphalt concrete we build on top. So we're raising pavement over the subgrade this way, and actually in open graded applications it provides drainage as well. But primarily again, how strong of a section we build and what's the function of aggregate in different ways that actually unbound aggregate when placed underneath an asphalt concrete and over a stiff foundation is what we will talk about, which is the inverted pavement design. Again, that's not exactly the design. I'm coming to that in time, but I'd like to show you one more time this load distribution curve. And most of the load is distributed such that we have less than typically 10 psi pressures going down on the subgrade, right? That's the pavement design philosophy in general. And a lot of the cases, thinly surfaced, low to moderate volume roads and thicker airport pavements. Now we have a lot to be gained by better understanding, better utilizing aggregate products. So we need to bring a full spectrum of sustainability solutions in the way that we're using and utilizing unbound aggregate materials. Having said that, when you look at the production in the quarries, a lot of those quarries, as I mentioned, they need to be moving into research and research that leads to advances in aggregate technology and innovative products and applications needed to target specific transportation projects. We need to bring sustainability by matching future regional needs with the availability of resources. Do we have in a project nearby quarries that will actually produce high quality aggregate for you? If not, where to go and how far? You all know that transportation is a big cost that comes into this. In the production stage, there is the conservation of energy and water and everything else that goes into the sustainability picture. There is the beneficial use of microfines and quarry byproducts. These are typically the waste material, byproducts generated from crushing operations and multiple crushing that takes place, right, for producing your unbound aggregate dense graded base course. One of the recent projects dealing with quarry byproduct, which I will also give an example towards the end of my presentation. So this is the production end. How can we use these aggregate layers, unbound aggregate layers, in a sustainable way by looking at the current needs and deficiencies or limitations or current sustainable alternatives to bring recycled material, local materials, other things. I have 3 slides to just highlight some of the points on these, because I will tie eventually these points to an engineered use of aggregate base, which is inverted pavement design. Okay, so when you think about most of the asphalt concrete surface and Portland cement concrete surface pavements, rigid and flexible pavements we look at, these are energy intensive bound layers, right? And there's a lot of carbon dioxide emissions and energy in the production of these surface layers. I say limiting the thickness. You don't have to go to maybe full depth, 16 inches of asphalt concrete if you use in a clever way, in an engineered fashion, unbound aggregate layers, in the way that you put these layers up. And inverted pavement will lend itself to that kind of an application. That way, maybe you can reduce some of the carbon dioxide emissions. Actually, a recent report that I was looking at, it interestingly gives a comparison of, in overall comparison between aggregate production and hot mix asphalt production. Of course, aggregates are needed for hot mix asphalt, right? What's the percentages of basically carbon dioxide emissions coming from which component in a hot mix asphalt? If hot mix asphalt is altogether per ton is about 50, the contribution of carbon dioxide emissions to that 50 is about 4. So aggregate production actually is quite sustainable compared to the asphalt binder, of course, and the HMA. So using high quality materials in the right places, say higher quality materials with thinner layers, that will help us achieve that perspective, right? Maybe using more of, again, aggregate materials with the good properties. But we also have the challenge of using a lot of local aggregates, because that's what we have in the immediate surrounding area quarries, right? And most of our quarries are carbonatic rocks. Maybe they're not as strong and durable as some igneous rocks and things. Local aggregates can be sometimes marginal, can be sometimes, but how can we actually make the best use of those? Well, in order to do that, of course, there are the environmental effects. If you're using local material, you don't have to transport, you minimize the noise, air pollution, human disturbance, those kind of things, but the transport cost obviously is the big thing in the final product. So if you're putting this material that's not the highest quality but local material under a certain thickness of asphalt, it's going to perform very well. It's not going to get a lot of stress on it, load on it. So there are some clever ways that we need to engineer uses of both the high quality and the lower quality materials to take full advantage of, and that's the kind of engineered use. Another example is, again, conventional aggregates versus these marginal natural materials as aggregates. As I said, better making use of those in the places where we don't get a lot of loading, maybe stresses, and they will perform fine, but you don't want to put them under very high loading conditions. We are under the challenge of reusing and recycling some of the old pavements. That's the common thing as we keep rebuilding and maintaining and rebuilding and rehabilitating old pavements. And again, recycling is a big thing that we need to bring in. So recycled aggregates, RAP, RCA, as well as quarry byproducts and wastes, as I talked about. We have to think about more of these bringing into our sustainable solutions. Recycling old pavements in situ, I think Tollway does this in the best possible way up there in Chicagoland. This is the kind of thing we should be always thinking about doing more and more. Finally, in the third slide of my sustainable solution ideas, that links back to the engineered uses of different qualities of materials, and we can achieve that by advancing our ways of characterizing the materials and understanding its properties, right? That really directly links to the topic of this seminars, which is the engineered use of aggregate base in the inverted pavement scenario. Interestingly, back in 2002, there was a scanning tour of the Federal Highway Administration, and a lot of that was observed in countries like South Africa and Australia. So, in the next slide, you will see about that scanning tour. It's the 2002 report from that international scanning program that they observed in France, South Africa, and Australia, some of the pavements that really outperform their design lives, and they're quite durable, they're quite long-lasting, okay, longevity. And what do they do to take advantage of those kind of different pavement designs and how we can bring them to the United States, to this country. That was the idea of the scanning program. And what came out as part of that scanning program was that I will show you two countries' designs, Australia's and South Africa's. And you will notice that they all build up from bottom up these pavements, as the case in autobahns and German technology, right? Like, look at this section, which utilizes different qualities of aggregate material in building up a somewhat, well, this is a flexible pavement. It's a flexible pavement, but just like your flexible pavement with surface treatment, right? It's actually a 2-coat chip seal, maybe not more than an inch on the top as an asphalt surface. And underneath that, we have up to 22 inches of aggregate layers. On top of the prepared subgrade, there's a lower subbase, there's an upper subbase. Again, qualities are going up from the bottom to the top. Maybe I should be using my mouse here for everyone. Lower, upper, and then base. Base quality is quite high because with that kind of a thin 2-coat chip seal, there's a lot of stress coming in this granular base, right? Better be high quality. This is Australian design. Building up from ground up, and then you don't have such thick asphalt concrete layers. Similar design is South Africa, and this is the inverted pavements. This is how they construct, actually, on top of their subgrade, about typical 6 to 8 inches, 15 to 20 centimeters of cement-treated subbase. But notice, 3 to 5% cement, right? What percent cement we have in concrete? 15, 16. You don't want to go too high in cement cut. Cement-treated subbase, which becomes a stiff platform to build this high-quality crushed stone for only 6 inches. And then 3 to 5 centimeters. That's up to 2 inches of asphalt concrete on top. And now I'll show you some examples from South Africa. This kind of a pavement structure, they're able to put 50 million easels of traffic. Okay? And this pavement lasts. How can they do that? Right. That's quite interesting. I will take you through that. Even I have a 5-minute video to show you if we have time on the construction. Well, it does work because they're doing it in an engineered fashion. They're taking advantage of all the good things in that inverted pavement design, and that way they're spending less money while getting the performance out of that road. They're green and sustainable alternatives because they're engineered alternatives. They make the optimum use of the compressive characteristics of the unbound aggregates, because if you look at this cross-section of an inverted pavement, really the neutral axis puts down below towards the subbase, stabilized subbase with a higher stiffness, puts the aggregate layer, that 6-inch of granular base material, into compression under the bending picture of the load. So that's how the compressive characteristics come into, and in compression aggregates, unbound aggregates are great. Not intentional, right? All right. Better compaction of aggregate placed over stabilized often goes up to 105% of typical Proctor densities. And their requirement is actually 88% of the solid density. Okay? That's how dense this layer has to be to perform. With that, less cracking and improved fatigue life due to lower tensile stresses, or in the asphalt, this is lower tensile stresses in the asphalt. That's the bottom of fatigue cracking is much less. And the reflective cracking potential is also minimized because you don't have a high cement percentage, 3 to 5%. That's lightly cemented. So not prone to shrinkage cracks because of the low cement content. It does a great job because subgrade stresses, deviator stress on top of subgrade from the wheel loads, very little. We're talking about 1-2 psi level, because it's already buried under a stiff subbase. The result is an improved pavement performance. Okay. So that's really the key about the inverted pavements. I have some slides that I'll go through that I borrowed actually from Dr. Maurice Deber from CSIR. This is their Council for Scientific and Innovative Research over in South Africa. And he was talking about the 7,700 kilometers of national roads in South Africa, giving a picture of that and telling you actually how they managed to build all these asphalt pavements, a lot of them inverted pavements, with a high quality crushed stone base by material quality as well as by construction quality, how they maintain to build those as high quality base courses. Okay, that's what they call as G1 base. And that's how on a road like this is typical main national highway here, 12 to 50 millimeters of asphalt on the surface, almost up to 2 inches. And you can get by with actually that thinly surfaced asphalt serving high traffic roads. From, again, 1997-98 in South Africa, base and sub-base types of national roads used. If you look at this spec, what they call as G1, G2, especially G1 base, is almost here 29%, and G1, G2 based on natural gravel sub-base is about 27%. So they have a large number of G1, G2 bases. The one that's on the top 29% is actually built on stabilized sub-base, which is the inverted pavement segment. So they have by majority an inverted pavement structure is primarily what they build as their pavement structure, right? Okay, what's a typical grading envelope or grading band for this kind of a high quality South African G1 base? They have a nominal maximum tap size of about 37.5 or 26.5. So 1 inch, 1.5 inch top sizes. Typically inches are here, see sizes, right? And these are typical densely graded bases for well-graded gradations. That's how they engineered them. And over the years, I just added this slide just to show you how they improved their technology over the years, going back to 1960s, and all the different steps in how they build confidence in that G1 base course for high traffic classes. Okay, and as you see, there were times the red arrows going down where they found some failures with crushed stone based performances. But throughout the years, I'm not going to go into details of this, especially using their HVS, accelerated pavement testing machine, right? How they were taking advantage of both the quality and the construction improvements to show the performance coming from that G1 base course in time. And finally, when we come to the green lines here from 1982, 1985, this is where they established that G1 base course material with that kind of thin surface on the top can serve 10 to 50 million easels for those kind of high type roads. How do they build it? What do they do? The amazing thing is that what this looks like in the photo here, or out here next to this hammer, you would think that this is concrete, right? No, it's not. This is an unbound aggregate base. How they build that base and how they test it with the head of a hammer, the ping, they call this ping test. The ping, you know, that they should hear as a concrete probably giving you that noise or yeah, that sound, right? This is the way they tested whether it was properly done as a high quality crush base. This is amazing. It surely looks like concrete, and there's a reason why it does. By the way, they have in the gradation all the way from 4 to 12% fines per sand passing number 200. So they're not getting rid of fines, and some of the fines can come at the up to a 4 or so plasticity index value. That's what they need to construct and compact in the first stage, this G1 base. But this is a dual phase process, as they mentioned. In the second phase, they have a certain slushing process. After compaction and obtaining maximum dry densities they come back and now they do saturation, slushing, putting all the moisture and slushing the fines out. During this process, they're actually getting all the angular rocks to orientate and interlock. And that interlock causes a solid density of up to 88%. That's the minimum requirement. Okay? This is like basically GS value of that rock, right? Times 62.4, that's the solid density for you. 88% of that. And that often exceeds or goes up to 105% with Proctor densities that we usually use, right? 105, because again, that aggregate layer is compacted on stabilized substrates, hard support. This shows you the different processes then, the different stages of the processes, but notice this thing, the wetting, the wetting and slushing, and that the rollers actually getting the moisture out and getting that moisture full of fines. Basically, they're flushing the fines out once they finish compaction. All right, there is a quick video here, if I can get that to run, to show you that process, which is very interesting.
The compaction process. The compaction process consists of firstly a standard compaction phase and secondly a particle interlocking or slushing phase. The standard compaction phase uses the customary method of compaction for gravel material to a minimum density level, which will allow the second phase to be executed successfully. The first phase of the compaction process should start immediately after the layer has been correctly shaped. The material should be at optimum compaction moisture content, ensuring that the matrix can be normally compacted to the minimum first phase density requirement. While some deviations to the basic approach to G1 compaction have evolved over the years, mainly being the solutions to variations in material quality, available equipment and local conditions, the original method will be described here. To start the compaction process, layer shaping is initiated by using a grid roller for 2 or 3 passes at a slow speed to gently knead the material into position without altering the gradation. Compaction is continued using the vibratory roller. The first pass is normally rolled without vibration, just to settle the material. Thereafter, rolling is done at a relatively high amplitude and low frequency for another 2 to 3 passes. The amplitude is then set to minimum and the frequency to maximum for a further 2 to 3 passes under vibration. Caution should be taken not to over-vibrate the layer and cause de-densification. Other non-vibratory rollers may assist, especially the heavy pneumatic tired roller. Note that the compaction rolling should start at the outer edges or lowest cross-section side of the pavement and progress towards the center or higher cross-section side of the pavement. Successive passes with the driving wheels leading to prevent bow waving of the material and corrugation formation should be applied in the same lane in opposite directions. Caution should be taken not to crush the particles and hence alter the gradation or to deform the surface. The density progression should be randomly monitored after each roller pass to quantify effectiveness and to identify non-productive rolling. The process continues with pneumatic tired rollers in combination with static steel-wheeled rollers to a density of at least 85% of solid particle density. The layer should have a well-knitted and uniform appearance with the correct longitudinal elevation and cross-sectional form. The second phase of the compaction process can now begin. The particle interlocking phase involves consolidating the material under saturated conditions by expelling or slushing out the excess fine material from the matrix, allowing the larger particles to interlock into a super dense matrix. The purpose of this phase of compaction is to knit the different sized aggregate particles into a super-dense interlocked mass by consolidating the layer and slushing the excess fines out of the matrix. The saturated fines also serve as lubricant in the process of reorienting and interlocking the larger aggregate particles. The layer must be saturated and slushed in relatively short sections of up to 200 meters, depending on equipment available on site. It is more effective to apply small amounts of water continuously than large amounts at longer intervals. It is advisable to apply the water to higher areas of the road and allow it to spread unaided to the lower areas. The shoulder should be breached to allow for the drainage of excess construction and slushing water. The fines form a finely textured, tacky film on top of the crushed stone layer. These must be swept off the road by hand brooms or mechanical rotary brooms. Towards the end of the slushing process, the expelled water loses its coloration, indicating that the excess fines have been removed. Air bubbles forming on the surface behind the roller wheels indicate that there are still voids in the layer. When the pneumatic tied roller leaves no indentation on the surface, it is a good indication that the layer has been slushed sufficiently. The process is ended by thoroughly wetting the surface again and brooming off the free water and any remaining slush without disturbing the interlocked surface texture. The layer should now have a uniform and firmly interlocked mosaic appearance and be allowed to dry off.
All right, I think that's the end of it. But it may sound to you like a cumbersome and long process, but the clever way of actually keeping fines in place to achieve the compaction densities in the first phase. In the second phase, now we don't need those anymore. Let's get rid of them by slushing, and that's exactly how you get that fines out. It's a beautiful process. I think really nice way of finally getting that like the dry layer, almost you're getting like a bound layer of concrete, which is what you see from the trenches. So this has been quite successful again, and there's some reports that were listed here on the economic benefits of HVS development work on G1 base that actually proved that a G1 basis built as such on stabilized subbases could go up to 50 million standard axles with only 2 inches of asphalt surface. Optimum thickness for the G1 base on a cemented subbase is 150 millimeters, 6 inches. And then also the stabilized layer is about 8 inches thick, is according to what they say is the optimized values. Now, if you look at some of the research and demonstration studies in the US, what people have done in this area over the years, this is where one of the very first studies done, my advisor, Dr. Dick Barksdale, in 1983, in their Georgia Tech, in their lab, under some plate loading, established 12 pavement test sections. Several conventional ones, full depth ones, but 2 of them were actually inverted type pavements. And I got involved actually in modeling behavior of these inverted pavements in my PhD studies. And that's when I developed the GTPay program. And therefore, what I will quickly show you goes back to 1983, what as early as in the early 80s, Dick Barksdale at Georgia Tech had found. The 2 inverted pavement sections went all the way up to 4.4 million load repetitions and exhibited better performance than the conventional and full depth sections, when actually they were built in a test pit out at Georgia Tech. And I ended up with the modeling of of these test sections, different tests that were conducted by Dr. Barksdale, which is about 3.5 inches of asphalt, 8 inches of unbound aggregate base, and that's the conventional setup basically, but the cement stabilized subbase was about 6 inches on 2 of those inverted pavements he also tested. So these are all the different locations that I was doing my modeling with anisotropic base
nonlinear, stress-dependent, all of those things that GTPay could do. That was my PhD work, right? And I was able to come up with responses predicted at various locations in the paper. Just to mention that the asphalt concrete was a typical Georgia DOT AC20 asphalt. Asphalt cement and asphalt binder, Georgia DOT B binder used. These are the specs, 19 millimeter mix. Subgrade was a typical silty sand A4 material from Georgia, from Atlanta area, compacted to 98% of T99. And then base course material was a granitic gneiss, which is a really nice hard crushed material. And the way it was paved in the case of, and compacted in the case of the inverted pavement sections up to 105% as reported. That was quite clear actually from the study. Two sections that I studied, section 11 and section 12. One was a soil cement subbase, the other one was an aggregate cement subbase. So little differences in the, again, you need to divide these by 7 for PSI values, I guess 1.5 megapascals or 8 megapascals unconfined compressive strength. So section 11 is a little lower in the strength property. When you look at the general performances of these test sections, clearly repetitions to failure, this was a plate load, basically repetition, not moving wheel load, okay? And they were changing the location of the really load on that plate location around just not to get a punching failure ever. Inverted pavements, those two sections went up to 44 million, and the others were not coming anywhere close. They lasted much longer. My duty, my job was to analyze from a mechanistic point of view, analyze these pavements, especially all of the pavements, of course, but I did that for inverted pavements. Here are some results of some of the critical pavement responses. On the top of subgrade, bottom of AC, radial strain, surface deflections. When you look at some of those actually measured responses, which my task was to model them again, these are all measured from the instruments installed, right? Pressure cells, strain gauges, so on and so forth. The lowest responses were always coming from the inverted pavements. So this is actually linked to the better performance. Of course, I did modeling of that. I'm not going to go into details, but these are some of the slides that I presented back in 1995. 23 years ago when I was a PhD student at TRP, okay? All right, well, that's the cross section of the FE mesh for getting those test sections of Professor Barksdale's, and we published that paper. Interestingly, when we look at the inverted pavement sections, this is the cement stabilized subbase, this is the unbound aggregate base. Looking at the lower ends of the unbound aggregate layer, usually that's where you get the tension. These are horizontal stresses. Nothing. These are all in compression. Again, compression is red and yellow all the way to 0 here. Anything going towards the blue colors from the yellow, 0, is in the direction of tension. So you don't see any tension in the horizontal direction in the aggregate base. That's a really good thing. And of course, we did study the different thicknesses of the cement stabilized base, analyzing for vertical stress on top of the subgrade. This is deviator stress, really. Understanding what thicknesses are adequate, and then doing more of conventional versus inverted pavement comparisons, right? You can clearly see that tensile strain at the bottom of the asphalt, always inverted, is giving lower tensile strains associated with, longer fatigue life for HMA. Looking at tensile stress at the bottom of the subbase. Well, soil cement being a little stronger layer, higher compressive strain, right? Aggregate cement being higher a little bit. So you're getting a little higher tensile stresses generated in the aggregate cement as compared to the soil cement as for horizontal stresses, tensile stresses. Finally, the summary of findings from my work at that time was that, again, we were able to model some of the much lower responses as obtained and measured from the test sections. I was able to show that compression all of our aggregate base was under compression, which is the best way to get the properties and most out of your aggregate base, actually putting it under compression. And sensitivity analysis that we did came up at 152 to 203, about 6 to 8 inches of base course. And that of the cement stabilized subbase was an optimum and economical inverted pavement design, which agrees well with many years, 20, 30, whatever, almost 30 years of experience of the South Africans. Other applications in the US. Louisiana is very well known for their famous stone interlayer pavement. Okay? And what that is really an inverted pavement. 3.5 inches of HMA, 4 inches of crushed limestone, 6 inches of soil cement underneath that. That's the same inverted pavement design section, right? Little differences in the thicknesses. Here is a report from 2001. They have their ALF machine, another accelerated pavement testing machine. And with the ALF, the stone interlayer system, they call it stone interlayer, the cement stabilized subbase. The pavements, inverted pavements, carried over 4 times the easels of the conventional pavements before failure. Again, whatever failure that they were looking for, fatigue or rutting. 54 projects actually constructed all the way up to 612 lane miles from 2003 to 2007. It's very highly favored in Louisiana. Now, it's also hot, warm climate in Louisiana, right? Not many freeze-thaw effects. When I checked with the northern states, there's always the question of Minnesota, Illinois here. Cement stabilized, shrinkage cracks. Well, again, if you limit it to 3%, cement stabilized subbase cracking on you a lot because it's not going to get as rigid, and you're minimizing the cracking potential with low cement. You don't want to exceed any time over 5%. Right? Georgia's experience. Very quickly, just some slides. This is an actual job that was done in 2001, and this was a job that received National Stone, Sand and Gravel Association's Capstone Award in 2001. This is the famous Blue Circle, Morgan County, Georgia Quarry Road. Okay, this used to be the Blue Circle Quarry, now it's called Lafarge, basically owned by Lafarge. Approximately 1.1 million easels were put on it from 2001 to 2009, and no rutting or cracking, excellent performance on inverted pavements. Conventional section has substantial cracking. Well, you will say, okay, this is a quarry road of an aggregate producer. This is not an official state highway road like the transportation agency, right? I'll get to a similar one in Georgia that was constructed by Georgia DOT as well. So in that road, they used both the Georgia DOT compaction and the slushing technique they tried, I believe. Here is a typical cross-section of the compaction method. According to Georgia DOT, they used 3 inches of asphalt, 6 inches of aggregate base, 8 inches of cement treated, and there is an interlayer of 2 inches of graded aggregate base filler and prepared subgrade. And they did both, as I said, slushing technique with the South African inverted pavement design, and this is Georgia inverted pavement design that didn't have the slushing. This is compared to the conventional pavements of the typical whole road of the quarry road. And these are FWD readings, deflections, okay, normalized deflections entering Lafarge Quarry. Look at the deflection levels. These are centerline deflections from FWD testing. Much lower. And even with the typical Georgia compaction procedure, they were able to achieve that, not the slushing. Georgia DOT took on the request of actually Georgia Crash Stone Association, and in this case, there is a LaGrange bypass near the city of LaGrange, south of the city of LaGrange in Georgia, that Georgia DOT constructed a certain 0.7 miles here as inverted pavement test section. That's the stretch of the actual project. Just to tell you where the project is, actually this is the city of LaGrange on this old Google map here, and the project is highlighted right here south of the airport, and this is the 0.7 mile That's inverted pavement section, test section, brand new pavement that was constructed as the bypass loop. And LaGrange, city of LaGrange is actually 67 miles south of Atlanta for you, to give you a perspective. Okay? Look at the test sections, typical cross sections. Inverted pavement section compared to the original design was in this case of Portland cement concrete, a rigid pavement section. So instead of 9.5 inches of PCC, 10 inches of aggregate base over on top of prepared 6-inch subgrade for a soil support value of 5, they went over to an inverted pavement design of putting rather thick 10 inches of cement treated base, 6 inches of aggregate, about aggregate base, and then 2 lifts of base and surface courses of super bay mixes, 2 and 1.5 inches. So this is a typical inverted pavement, right? The only difference from the South African is about maybe 2 inches thicker here. There are some construction pictures of this road. In some cases, actually, the subgrade conditions were not that favorable. They had to do subgrade improvement by blending with aggregate. This is still the subgrade because they had to achieve the SSV value, subgrade soil support value of 5, right? Ohio DOT also uses this. So that's what they were doing, subgrade construction, and this is finally the base course construction on top of that. Notice that South Africans did not show in the picture paving with a paver, the aggregate base course. Right? They're actually paving. In this case, well, this paving is operated sub-base directly on top of the subgrade. This is paving of the 10-inch stabilized subgrades. But in the South African practice, they now talk about also using paver to build a graded base as well. So that's some option to be further explored in the future. Again, some more pictures from the LaGrange bypass. Right here, the final road as built inverted pavement section, and the comparison with what it would cost if they constructed in that location a PCC pavement versus what inverted pavement costed. This is a net 30-year life cycle cost estimate of about maybe 139,000 net savings. That's what they reported in this case. Well, the final thing that I'll talk about here is a more recent Lockstone is a major quarry. They're a stone quarry company, but Lockstone had an expansion project of their Bull Run quarry in Manassas. I think this is where it is, at Highway 659 bypass in Virginia, just outside of Washington D.C. Okay. And Randy Weingart is the director of their materials, was the director of their materials management and product research with Lockstone. A few years ago he retired. He's now with National Stone, Sand and Gravel Association. And Randy's really led a big effort bringing industry and Federal Highway Administration together, plus researchers like us, to actually do a demonstration project where they had to expand operations of that quarry, but they had to cross over, go over a state highway, and they could only take the other side of the state highway. Was still their quarry land, but they couldn't expand unless they had to realign the state highway route. Okay, and for that they took the task or job of basically paying for that realignment as the quarry owners. So if you look at a quick picture of the quarry operation, this is the quarry, Bull Run quarry of Lockstone, and this is the highway right here. So the highway had to go over to a bypass like this circular loop. In this case, this is part of it is now being constructed, as you see. And right here, the yellow zone is where they wanted to put an inverted pavement test sections to demonstrate. And of course, because of the realignment now that allows them for expansion, so they had to chip in and actually build the road and get support from Virginia DOT working with them. But it wasn't just the Virginia DOT. They extended their arms over to Federal Highway Administration, Turner Fairbank Lab, and some of our friends from Turner Fairbank. They came partnered in this effort with actually funds put forward for instrumenting the inverted pavement test sections. So this was all based on the efforts through ICAR that we came up with actually an isotropic cross-anisotropic model to do the best characterization of aggregate base layer, and especially build on top of this time inverted pavements, right? The original section looked like that. The inverted section looks with the cement treatment right here. The original heads also cement treatment in this case, but a similar section that you can see skipping now the open graded drainage layer, and the bituminous base is actually replaced by an unbound aggregate base in this case. Okay, and that's what made the changes in the inverted pavement section. I was involved in a one-day demonstration project they did back in 2011, and I was there also presenting. This was in Manassas, Virginia. There was on the site, we ended up seeing a lot of the construction on site, as well as some of the instrumentation that FHWA was installing. We were able to monitor some of those things again on site. So these are from those efforts, some photos to share with you. And that's the instrumentation. This is the strain gauges for asphalt, right? And then there's Nelson Gibson at that time with Federal Highway Administration, and then Steve Weininger also here, some other researcher colleagues, again from University of Texas, El Paso, Reza Ashtiani is there. So some of you again very well know these people. And this is, as part of that, there's demonstration of the different gauges, the instruments, strain gauges, pressure cells, as well as Virginia DOT actually came up with their traffic counting system, the main motion system that was also installed by Virginia DOT on the site. So this is a compaction demo that they did on the site with nuclear gauge, Sencon, and so on and so forth. Of course, FWD testing. There was all the data collected from the bull run test sections. I don't have that. Hopefully, we will have Randy Weingart here for future CAN seminars to talk more details about what they found from all that study. But clearly, a cost calculation, cost comparison that they did was showing that inverted pavement section had a 22% difference in cost and was cheaper actually to build the same type of typical compared to the Virginia DOT design, their typical designs. The last item that I'd like to talk about on inverted pavement is that we took the advantage of taking this technology to be tested in our backyard right here. And that relates to the current project we are just finishing up. We just finished actually. The report is up on the internet, on ICT's publication page. You can download it. This is a study that I partnered together as investigators with Dr. Hassan Uzair, with Hassan, and Issam was the graduate research assistant. So how can we use quarry byproducts in sustainable applications, right? We know that quarry byproducts are waste materials, but that's not how the producers look at it. This is good material, sand-size material, anything passing 6 millimeter size, right? Typically less than number 4, sand-size material. When we did original work on that in the 125 project in the lab, we were able to get the 10, 11 psi unconfined compressive strands up to 30 times increase by going with 2% cement and 10% fly ash. Okay? So the good thing about this was, with that kind of encouraging result, how can we put the use of quarry byproducts to test in our full-scale validation study? And that's the 168 study that I mentioned to you, which considered these 4 different alternatives. And one of the alternatives, as you can see, is right here, the third one. The third one being stabilized subbase with quarry byproducts. Basically using quarry byproducts as sand size, and then stabilizing it with cement and fly ash, and putting a granular base on top, and something like 4 inches of asphalt on top, right? So that's an inverted pavement we also built in our cell 3, and that's the configuration right here. So basically, just to report to you how those inverted pavements performed, well, we know they would perform well because we did the material tested in the lab with the different options of 3% cement and 10% fly ash. And these are pretty high compressive strength numbers here. Okay, and we know they were going to do a good cement stabilized subbase for the inverted pavements. It's always a challenge if you're doing a project, very short test sections, how to do the proper batching, and we had a great contractor who worked with us diligently. And the way that actually we proportioned all the materials for a byproduct and the cement percentages and how we brought them together in our backyard in the parking lot and with a tiller paved it down as stabilized layers, I think that was a wonderful experience in the quality control especially. Surely quality control showed, like you were looking at the inverted pavement with cement, inverted pavement with fly ash, they're showing quite good modulus properties, acceptable modulus properties for the stabilized subbase in this case. Okay. There's more of this you can find from the report, but when we started running the Atlas, again, I'm sure all of you have seen the Atlas wheel running. Not sure if this will work now. Oh no, I don't have that video. But that's how we tested the constructed test section with 4 inches of asphalt on top, and we were using the laser profilometer here to get the profile readings. This is Issam doing that on a platform section actually. We went all the way up to 135,000 passes, and even after 100,000 passes, we increased the load level from 10 kip to 14 kip, which is right here, just to accelerate the rutting process. Okay, what you're looking at here is from cell 3, basically these two are the cement stabilized layers, 6 inches of aggregate base underneath, 6 inches of cement stabilized, or 6 inches of fly ash stabilized. So when you look at overall, at the end, 135,000, this is the fly ash stabilized inverted pavement. Right about a little over 12, maybe 13 millimeter or so. At the end of 135,000 passes at the high load levels of 14. The cement stabilized inverted section goes, this is the green one right here, and much lower than that. Indeed, these are the cross sections. This is the cement stabilized subbase cross section in our backyard. This is aggregate base, right? Just only 7 millimeter rutting out to 135,000 passes. I think this is very adequate for local agency construction. Right? Low volume road, local agency construction. I think this is a great construction. Typical pavement section to construct. Even in the case of fly ash stabilized, which was less stronger or weaker than, of course, the cement stabilized one in our case. We found the 13 millimeter around 0.5 inches is, I think, still a good target for really harsh 135,000 and the last 35 at 14 kip loading. Overall, I think inverted pavements do very well. I know I'm coming to the end here. It's about an hour now. But I want to mention to you in one slide what others have been doing and where we are with the inverted pavement section. This is the last slide. Tennessee DOT looked at the 1.7 mile road that was led back in 2012. And New Mexico DOT did another one also in 2012. And this is now finished, of course, and this we're getting really good data out of how these inverted pavements New Mexico constructed has been performing. About 3 years ago, there was a great session at TRB on inverted pavements put together by AFP7, the aggregates committee. And a fellow, an engineer from New Mexico DOT showed the good performance of this inverted pavement section, which is at a rather high altitude, 7,800 feet elevation. They get really harsh winters, even in New Mexico at that elevation. And inverted pavements didn't show signs of crack. I think that's a good thing. There's a potential pool fund project statement that's been going around for several years. That's still a potential. There's recent interest of Georgia Tech and Georgia DOT researchers to do more with inverted pavements. And also in the past 5 years ago or so, I believe Vulcan Materials had another demonstration project in North Carolina that showed really good performance of inverted pavements. Altogether, I think inverted pavements is a good alternative. It's a sustainable alternative. It utilizes engineered application of an aggregate base over a cement stabilized layer. And when everything is constructed right, you've seen examples. This is a truly winner pavement test section construction technique and an alternative, design alternative. Thank you very much for your attention.
Does anyone have any question for Professor Tutumluer?
So I think it was right when you introduced that South African section with the slushing that talked about a surface treatment of 12 to 50 millimeters. That 12 millimeters that's probably not an HNA, right? You had said something about a chip and seal type thing. I just couldn't even see practically how you could put down half an inch.
That's right. The question was, again, in the South African practice, 12 to 50 millimeter surfacing on top of the aggregate base, which is supposed to be an asphalt surface, right? The 12 millimeter is our surface treatment, basically. Whether, two layers, two chips, layers, or one, but it's just 0.5 inches, basically. That's not a structural layer. Even the 2-inch goes back to, if that's a structural layer, even the 2-inch or 50 millimeter one would be a thinly surfaced pavement consideration, where actually bottom-up fatigue cracking is not a problem because it conforms to the shape of underlying support. Again, fatigue, bottom-up fatigue, as we know, is not a problem. So I think that's where they come. But the 12 millimeter is surface treatment.
Thanks for the presentation. So I was wondering if you have any field data, like the distress field data, that compares inverted pavement with the conventional.
Well, I showed some of the performance tests that were collected over the years. I didn't show you actually some of the performance photos. Hopefully we can get more seminar speakers to come here to tell us for those specific projects in the future. But yes, especially the Bull Run project collected a lot of data, and I think you're asking more instrumentation data from pavements, right?
No, field data, like distress, like cracks.
Oh, cracks, yeah. In all those projects, again, if we go to the right person who was in charge and who was responsible, which we are hoping to be able to bring those as speakers, they will be able to share with us a lot of the performance data, how pavements perform. But in some of them, as I mentioned, like 2001 to 2009, that was reported in 2009. After 8 years, conventional had a lot of cracks inverted to them. That was the Lafarge quarry, whole road, basically. So things like those, we've been collecting data over the years.
Thank you, Professor, for that. I have 2 questions. First question is, like, since we see in case of inverted pavements, we need high quality aggregates, and that too, like, more larger quantity, like thicker sections. So first is, like, does it have a practical implication of availability of aggregates, like high quality aggregates? But that will probably limit the use of inverted pavements if you don't have.
That's a good question. Like, for example, I think in your question you're comparing high quality versus kind of medium, low quality aggregate, not that high quality. High quality, let me say high quality, we like to go to hard rocks too, like igneous, trap rock in Wisconsin, I don't know. Right. Great granite material over in North Carolina, wherever, or Georgia is also the same that from Georgia Tech's experiment, they had a good quality, high quality igneous rock, or type, hard rock. That's an excellent question. Again, I think Georgia had the same kind of granite, Georgia projects. We need to check back whether some of the sedimentary rocks, some of the carbonatic rocks that mostly are produced, limestone, dolomite type, mostly what we have in Erol, how they will be going through the compaction process, but if you had to do the slushing, for example, how they would survive and how they would lock up, like the interlocking after slushing they were talking about, right? That's very, very interesting question. I don't know the answer to that. We need to experiment more with that. However, what we know is that although Georgia DOT typical design was applied in the whole road
section. There was a slushing technique that they tried to actually apply it. And the typical compaction of the aggregate base, according to Georgia DOT standards, they both were quite low with the FWD deflections. So whether or not we have to go through the slushing, we may not be able to do slushing as good as the South Africans, but even the typical base course construction we do with it, achieving high enough density, may be enough because we're achieving quite high densities now over a stabilized base, or subbase. So the base course goes up to very high densities. So I think that still brings out the good qualities of aggregate. Not the highest quality, but maybe medium quality, but it will still be at the, unless it is crushing, again, it will perform very well.
And the next question I have, so as we saw the example of South African case where like just you have a 12 to 15 millimeter of like chip seal kind of
Two-coat chip seal, I think that's
two-coat chip seal. So like since you have a lot of aggregate structure underneath, can it cause freeze thaw issues? Like since you are doing the slushing, you're removing the fines, so now there are like interlocks have worms probably, and then if there's a freeze thaw issue,
That's another good question. Freeze thaw is usually an issue with the stabilized layer, right, for durability, than the unbound aggregate layer. So I don't think there has been a concern ever on the aggregate base for durability or freeze thaw issues. It's more the stabilized layer, if high cement content and opening up large cracks. But that's an excellent point. Now, even in that case, if you go back to some of the semi-rigid designs, like for example, heavy-duty cement stabilized base courses in China they built, which has been a classic approach, right? Under asphalt concrete, putting a high cement percentage cement stabilized base, and of course that has very drastic consequences, which are large cracks coming into the asphalt. And what they did, and I know this is a fact, they started putting an interlayer of an unbound aggregate on top. So they really pushed their base courses, heavy-duty cement stabilized, to sub-base. And they were able to prevent some of the reflective cracking in the asphalt by putting is an interlayer of unbound aggregate on the asphalt in China. So again, with 3 to 5% cement, the cracking, if you ever get cracking in cold northern climates, it's not going to be reflecting to asphalt with the 6-inch aggregate base under the asphalt first. That's my opinion.
Any more questions? So let's take Professor.
All right, thank you very much.